Okay, 5.9 notes, graphing radical functions. So here we go. Before we graph, we didn't get to this on the last video, so I'm just going to show you real quick how to do that. So what you're doing here is you're going to simplify each of these problems, and we have 3 examples here, by combining like terms. So if you look at the first problem, we have 5 times the 4th root of 3 minus 8 times the 4th root of 3 plus 2 times the 4th root of 3. They all have the 4th root of 3 in common, which means they are like terms. So to combine them, I just add their coefficients. So I do 5 minus 8 plus 2. Now 5 minus 8 is negative 3. Negative 3 plus 2 is negative 1. So my answer is going to be negative 1 times the 4th root of 3. So notice that the 4th root of 3, it's still there. I just combine the numbers in front. And we all know that we don't have to put the 1 here, so this can be rewritten as negative 4th root of 3. Let's go ahead and do this problem. Now here I have the cube root of 2 and the cube root of 54. Now they have cube roots, but the numbers inside are not the same. We need the numbers inside to be the same. What we're going to do is, we need to know our perfect cubes. So if we look at our perfect cubes list, or if we know it by heart, 27 is a perfect cube. And 27 times 2 is 54. So what we're going to do is, our first step is to do this. I'm not changing the first radical, so I'm just going to bring down 2 times the cube root of 2. I'm going to bring down the plus sign. I'm going to bring down the 3, but on the inside of these parentheses, I'm changing the cube root of 54 into the cube root of 27 times the cube root of 2. Okay? Now, why do I do that? Why do I split this up into this? Because the cube root of 27 I'm going to replace the cube root of 27 with 3. Now, if you don't know how I got 3, it's what times what times what is 27. That's what that's asking, and that's 3. You can also plug it into your calculator if you're really unsure. So this becomes 3, and this comes out as cube root of 2. Now, before I go in and add these like terms, I want it right here. I want to do 3 times 3, and that is 9. So I'm going to bring down 2 times the cube root of 2, bring down the plus sign, and 3 times 3 on the outside of the second cube root is 9. Bring this down. And now this problem is just like the first problem. I have 2 cube root of 2 plus 9 cube root of 2. 2 plus 9 on the outside is 11. And I just keep the cube root of 2. And that's it. Here we have x to the 2/3 plus 3 times x to the 2/3. Well, we assume there's a 1 here, and so this problem is very easy. 1 plus 3 is 4, x to the 2/3. Okay, so now let's actually get in, so we'll review this in class. So let's actually get into the graphing. You're going to want to copy this down real quick, so I'll take a moment to pause, copy this down. Okay, so you've copied this down. Just to look at it real quick, we have A is the vertical stretch, and H is the left-right shift. K is the up-down shift. This should look familiar. We've seen this in multiple different units before. We've done it with parabolas and with other functions. So now we're going to be looking at 2 types of functions, the square root function and the cube root function. Essentially, the only difference between these 2 functions is what the root is. Here is the square root, which we know the root is 2. And here the root is 3, and that's what makes it a cube root function. And then I just told you, remember that H lies and K tells the truth, our little trick to doing this. Go ahead and take a moment to pause the video again. Pause the video again and copy this down, and I'll explain this to you as well. Okay, so we have what's called the parent functions. We've seen the idea of parent functions before. So we're going to look at both the parent function of square root and cube root. So the parent function of the square root, is the most basic square root function you can have. So we have f of x equals the square root of x. There's no other numbers. It's just the square root of x. So what I did was I made this chart over here, x, y, and what I did was I plugged in numbers, but I didn't do 0, 1, 2. I did 0, 1, 4. Why would I choose 0, 1, 4 and not 0, 1, 2? Well, think about the kind of function we have. We have the square root function. I think it would make sense to plug in numbers that are perfect squares, because we'll get nice whole numbers back. If I plug 0 in for x, what's the square root of 0? So my input is 0. If I plug 0 in, my output is also 0. If my input is 1, the square root of 1 is 1. If my input is 4, the square root of 4 is 2. So I picked numbers that will plug in nicely into the square root function. Then I graphed these points. And so the graph of any square root function takes on this shape right here. One thing I want you to notice is that, oops, sorry. Oh, it's in marker. Darn. Oh well. Your square root function always has a definite starting point. And then the next point over, assuming no vertical stretch, is up 1 over 1. Okay? Then the next point is up 1 and over 3. And then we have the domain and range. The domain is x is greater than or equal to 0. Remember that domain is all your x values. And if you look at your function here, on the x-axis it starts at 0, and then it never stops. So it's all x values greater than 0. Same thing with the range. The range is all your y values. Well, on this function, this graph doesn't start until y is equal to 0. And so the graph starts at 0, but it slowly goes up forever. This actually does go up forever. It's just a very slow process, though. Let's look at the cube root function. So we have f of x equals the cube root of x. I made a table for this one, and what I did with this table is we are allowed to have negatives inside of odd root functions. Odd root. So, 3 is an odd number. So I'm allowed to plug negative numbers into the cube root of x. If you plug negative 1 into the cube root, you get negative 1 back. I could even go further. A perfect cube is also 8. So I can plug 8 or negative 8 into this. If I also plug negative 8 in for x and take the cube root of that, the cube root of negative 8 is negative 2. I won't show that on here, but anyways, you can plug 0 in. The cube root of 0 is 0. The cube root of 1 is 1. And I plug those points in. So this function, it looks a lot like a square root function, how the shape is right here. It's just that now we're allowed to go this way as well. So the cube root function has this shape. Now, how does that affect your domain and range? On the square root function, we had a definite starting point, and that's why we were limited. But here, our graph goes forever in both directions. So it covers the whole x-axis, and so that's why my domain is all real numbers. It also goes down forever this way and up forever this way, meaning my range is also all real numbers. So I'm going to show you how to graph these using transformations, and then we'll be done with this video. So, example 1, we're going to graph f of x is equal to the square root of x plus 1 plus 3. We'll state its domain and range. We'll state the domain and range right here. Then we're going to graph a different function, but if you can tell, they are the same function. It's just that g of x has a 2 in front. And then we'll compare the two functions. Okay. What I'll do is I'm going to kind of color code this thing. For f of x, we're going to do it all in orange. Let's see if orange shows up nicely on here. Oh yeah, it does. Okay. We'll do f of x, any work for f of x in orange. And for g of x, we're going to do it in green. Okay? So let's start off with f of x. For f of x, because we have a plus 1 on the inside, that's our h value. Now, h shifts left and right. It's plus 1, so you would think it shifts right. But because h lies, it's actually, this function is going to shift to the left 1. Now plus 3 is on the outside. If you compare it to your parent, to the function, that's your k value. K tells the truth, so this is really plus 3. Because k is your up and down shift, we're shifting up 3. And then I have no number here. I mean, well, there is a 1 there, but because it's just 1, there's no vertical stretch. And I just realized I wrote over the space to put my domain and range, so we'll fit it in somewhere. Okay, let's go ahead and graph. I'm going to graph the points also in orange. So think about what your parent graph of the square root function looks like. It looks like this. So what we're going to do is we're going to go from 0, 0, and we're going to make the movements that we just said. We're going to go left to 1, but also up 3. So left to 1 and up 3, and we're going to put that point right here. So what is that point again? If we look at this other, at the parent function, it's these 2 points. These 2 points are identical in what they tell us. So then how do I get the next point? Well, remember what I said, you go up 1 over 1. So here as well, I'm going to go up 1 over 1 to get my next point. And then to get the third point, we have to go up, well, it depends on where you want to start from. If you want to start from the original point, you have to go up 2 and over 4. So if I go from the first point I drew, you go up 2 and over 1, 2, 3, 4, right here. And then you just draw the same shape that we have right here. So we draw this shape like that. And so that's the graph of f of x. This is a graph of f of x. Let's go ahead and do domain and range. I can't believe I wrote over that. So I'll just do it again right here. Domain and range. I apologize for that. So your domain and range, for the domain, it's all your x values. If you look on the x-axis, this function starts at -1. So that means that and then it goes on forever. So we're going to say that our domain is all x values greater than or equal to -1. And then our range for f of x, well, this graph doesn't start on the y-axis until it hits 3. That's our lowest point, and so our lowest y value is 3. But once we hit 3, the graph goes up forever, meaning infinitely. So it's all y values greater than or equal to 3. Let's go ahead and do g of x. Like I said, we're going to do that in green. So actually, g of x has the same exact shift, left 1 and up 3. But this time it also has a vertical stretch of 2. So that means it has the same starting point right here. So I'm going to go ahead and just draw over the original starting point. Because it has the same shift left 1 and the same shift up 3. But what does the vertical stretch do? What the vertical stretch does is instead of going up 1 over 1, like we did to get to the next point, we're going to go up 2 over 1. Like that. Okay?